Hello, everyone. My name is Michael Kearns, and Salone Barokas kindly asked us to record a brief video about our recent work, which does indeed seem related to the interesting topic of your workshop. This is joint work with my Penn colleagues Seth Neal and Aaron Roth, and Stephen Wu, who's a postdoc at Microsoft Research in New York City. And the title is Preventing Fairness Gerrymandering, Auditing and Learning for Subgroup Fairness. There's a preprint available on arXiv, which we're updating as we improve and refine the results. So as people in this audience probably know, when one talks about definitions of fairness for algorithmic decision-making and machine learning and statistics, it's typical that one identifies one or more attributes or groups that you're concerned about discrimination for, such as race, gender, and age. And importantly, it is usually the case that one needs to specify these protected groups or features in advance. And then one applies fairness notions that are usually statistical in nature. So as examples, there's the notion of statistical parity, which, let's say in the case of lending, would ask that there are approximately equal loan rates across these groups that we're protecting, ignoring creditworthiness. A more refined one actually takes outcomes into account, or creditworthiness or merit, such as equality of false positive negative rates. There's also calibration, where if we estimate that somebody is 30% likely to repay a loan, that of the people that we classify as 30% likely, roughly 30% do repay. So these are all statistical notions of fairness that are applied to one or more attributes that you're concerned about protecting. And importantly, and our primary concern, is the fact that no promises are made to specific individuals or even to finer-grained groups. In particular, related to intersectionality, by a finer-grained group, I might mean something like a combination of features like black women over age 55. Okay, so each one of those features is protected individually, but there may not be protection provided to subgroups defined over those same attributes. And as a toy example of what we're trying to get at, just imagine a setting in which there are two features that we'd like to protect. And just for simplicity, let's imagine that they're binary, like race, let's say black and white, and gender, male and female. And imagine that these two features are uniformly distributed in some population. So all four combinations of these binary features are equally likely. So if I have a classifier that labels somebody positive, let's say gives them a loan, if they are either a black man or a white woman, this classifier is actually fair at the group level when I look at either one of the protected groups in isolation. Because if I look at gender, men and women are positive 50% of the time. And if I look at race, both black and white subpopulations are positive or given loans 50% of the time. But of course, by design in this example, if I look at any combination of two attributes, such as black women, then I will violate statistical parity as badly as is possible. Okay, and so this possibility and phenomenon is what we're terming fairness gerrymandering in the paper, and the gerrymandering part refers to this idea that you might achieve fairness at some higher group level by discriminating against some more complex subgroup over the same protected attributes, okay, such as black women over age 55. Interestingly, Facebook has a hate speech policy that's trying to get at this issue by declaring that there's a policy against hate speech not only for a number of individual features in isolation, but also for combinations of them, such as black women over age 55. And like everything else in machine learning and statistics, if I design an algorithm which is meant to be fair at some macroscopic group level, there's absolutely no reason to believe that it will be fair in this stronger sense that we're talking about, in the sense of protecting against subgroup discrimination as well. And I'll show shortly that in fact on real data sets this actually happens. And this is just an instance of the general phenomenon that in machine learning, if you don't explicitly put something into the objective function, there's no reason to think that it will be obeyed. Okay? So what we'd like to do in this work is to try to provide stronger guarantees of algorithmic and statistical fairness that does provide protection for more complicated, rich subgroups. There's a limit to how far one can go in this sense, however, because if you think about it, if I'm using a statistical model which is bound to make mistakes sometimes, then of course if I look at sufficiently refined subgroups, namely specific individuals that were treated incorrectly by the model, so somebody was falsely denied a loan, that individual consists of a subgroup of size 1 that has experienced discrimination. So we need to find some kind of balance between the more traditional crude notions of fairness at some macroscopic group level, while understanding that we can't go all the way to promising that we'll never make any mistakes at all. And that's what we try to do in this paper. And so I apologize for the dense notation in the following passage, but this is a brief description of the model that we have in mind. So as is usual in statistical models for algorithmic decision making, we're imagining that individuals in a population are represented by feature vectors, that here we're actually dividing into two components that I'm calling x and x prime. Think of x as being the features or attributes that we're trying to protect, like race, gender, and age, and x prime are all of the other features that we know about individuals, which may be correlated with the x's, but are not specifically part of the features that we've declared that we're trying to prevent discrimination for. And there might also be some outcome variable that we're trying to predict y, such as whether somebody will repay a loan. And so an individual is represented by a triple consisting of their protected attributes, their unprotected attributes, and their outcome. And we're imagining that these triples are drawn from some population or probability distribution P. And now imagine that we have some model or algorithm that I'm calling H that's trying to make predictions about this outcome Y on the basis of both the protected and unprotected features of individuals. And let's also introduce notation for subgroups. So G of X is simply a function which indicates whether a particular individual with protected features X falls in some subgroup, again, such as black women over age 55, okay? And so our definition of what it means for this statistical model H to be fair with respect to this group is quantified by two small numbers that I'm just going to call A and B here. And we say that H is AB false positive fair with respect to G if whenever the group has sufficient mass in the population, so whenever the probability of membership in the group is at least some minimal amount A, we have the following inequality, which is basically saying the false positive rate doesn't change much when we condition on falling in the subgroup G. So this first expression here is just the false positive rate of the model or algorithm H unconditionally in the entire population. And this second expression, which I've highlighted the conditioning in red, is the same quantity, the false positive rate of H, but conditioned on membership in the group G. And so what we're asking here is that anytime we look at a group that has sufficiently large representation in the population, maybe it needs to be, let's say, at least 1% of the population, we have that the false positive rate in the overall population and in the subgroup is controllably close, let's say has a difference smaller than 1%. And I've given this definition with respect to the notion of false positive fairness, but the results and definition equally well apply to the other notions of statistical fairness that I described on the last slide. Okay? So this is the definition, but this is the definition for a particular subgroup G, such as black women over age 55. And now our interest is in classifiers or algorithms H that meet this definition of fairness, not with respect to some particular predefined subgroup, but with respect to some rich class of subgroups that I'm going to call capital G. So you might imagine, for instance, so far I've been really talking about kind of conjunctive subgroups where I identify these protected attributes like race, gender, and age, but I also want to protect against all combinations of those conjunctions. But you can imagine other types of subgroup representations like linear threshold functions or whatever your kind of favorite parametric class of statistical models is. Okay? So this is kind of our goal. Our goal is to design models that meet this stronger definition of fairness that protects subgroups in some large class of subgroups. And we're generally imagining that this class of subgroups G is large in the sense that it's too big to enumerate. It's it's something like all possible combinations of features from your protected attributes. And so this definition leads to two interesting algorithmic or computational problems. One is auditing. So what do I mean by auditing? So the auditing problem simply asks, if I'm given access, black box access to some algorithm or statistical model H, so I get to see the protected attributes of individuals, the decision made by the black box algorithm H, and the outcomes Y, can we decide whether this algorithm or model meets this definition of fairness, or instead can we find that it violates fairness with respect to some particular subgroup in the class G? And perhaps even more interesting is the problem of whether we can design learning algorithms that indeed will meet this notion of subgroup fairness. And so let me tell you a little bit about the theory of both of those problems. And again, these are adapted from a more technical slide, so I'll try to kind of talk around the terminology that many of you won't be familiar with. So the first theoretical result is that essentially auditing a given statistical model for fairness with respect to a class G can really be recast as an equivalent learning problem for the class G. In particular, it's equivalent to something known in the machine learning literature as weak agnostic learning of G. So, in other words, the problem of determining whether a given statistical model meets our definition of fairness actually can be cast as another instance of a machine learning problem. Okay, and this holds for all the different notions of fairness that I mentioned on the first slide. The impact of this, or sort of relevance of this theorem, is kind of a good news, bad news aspect. So if you know the machine learning literature on weak agnostic learning, in the worst case, this is a very computationally difficult or intractable problem. And so the negative part of this theorem is sort of saying that in the worst case, the auditing problem might be very difficult from a computational perspective. On the other hand, the fact that this problem is difficult in the worst case theoretically has not prevented the machine learning community from developing very, very powerful heuristics that work very well in practice. And so the flip side of this equivalence is that we can use those same heuristics for solving this auditing problem. Okay? I think the more interesting aspect of the paper is the design of algorithms that meet this subgroup fairness learning definition. And in the paper, we describe a general formulation that treats the problem of designing a learning algorithm that meets fairness with respect to a class G as a two-player repeated zero-sum game in which we think of the learner as having some strategy space consisting of statistical models that they're trying to use for accurate prediction, and the auditor has a pure strategy space which consists of some class of perhaps complicated rich subgroups that they're trying to protect discrimination against. And the learner's objective is essentially to minimize the error subject to approximate fairness with respect to G. And so the way this game works, if you like, is that at each round, the learner is kind of proposing a statistical model from their class. The auditor then finds a group which is being discriminated against by that statistical model of the learner. And then the learner adapts their objective function to explicitly then try to provide fairness with respect to the group that was found by the auditor. And this game continues with the objective function of the learner gradually being asked to protect against more and more subgroups from the class G. And for instance, there are a number of ways of implementing this zero-sum game framework as an actual learning algorithm. One, but not the only way, is to have both players use something that's known as fictitious play. But for this talk, I think the important fact is that you can actually design such algorithms and prove theoretically that they converge to a statistical model for the learner that is fair with respect to the class G of subgroups that you're trying to protect and minimizes the predictive error subject to that very strong fairness constraint. Okay? So it's one thing to design and propose such algorithms. The question is, just how strong a constraint is this notion of fairness with respect to the class G? In particular, I can design an algorithm that will meet this definition of fairness, but maybe the constraint is just so strong that the predictive accuracy of the models produced by this algorithm will be very, very poor. And this, of course, is not a theoretical question. This is an empirical question. And so let me describe to you the initial set of experiments we did to investigate it. We looked at the well-studied communities in crime data set. This is a data set in which each of the individual records is not the representation of a specific person, but rather of a community in the United States. And there are a number of attributes describing each community. The Y value that we're trying to predict here is the rate of violent crime in that community. So we basically call the positive examples, if you like, the communities that are in the 70th percentile above for violent crime rate. The features consist of 122 features total that have to do with all kinds of demographic properties of the community in question. And we designated 18 of these as being protected, and all of them have to do with race in some sense. They basically describe for the community the percentage of each racial group amongst roughly 5 racial groups, the per capita income of those groups, the racial makeup of the police in that community, and the fairness notion that we're applying in these experiments is false positive rate. So this is a nice data set for us because the number of protected attributes is relatively high. So there's 18 protected attributes that are essentially can change independently of each other. And when you look at kind of rich combinations of 18 features, you're getting a very, very large number of protected groups. Okay. By the way, on this topic of whether this fairness gerrymandering can happen if you don't explicitly try to design to prevent it, on this data set, for example, if we just ask for kind of protection via false positive fairness for the 18 features separately and basically get that for each one of those 18 features in isolation, the disparity between the false positive rate on that subgroup and the overall population is smaller than, let's say, 3%. So that's kind of a model that's fair with respect to the traditional notion of false positive fairness. Well, if you audit the model found by meeting that macroscopic definition of fairness, you immediately find a subgroup which consists of 67% of the population in which the false positive disparity rate is over 25%. So the fact that we protected at the individual group level down to the 3% mark did not prevent us from finding a very, very large subpopulation that was experiencing much, much higher discrimination. So this gerrymandering is a real issue, including with traditional machine learning approaches. Okay, the classes of models that we used for both statistical models for prediction and for subgroups were linear threshold functions, and we implemented our algorithm, as I mentioned before, using fictitious play. There is one free parameter in our algorithm which essentially can be viewed as setting the relative power of the auditor over the learner. So if you set this parameter that I'm calling capital C to be very, very large, you're giving the auditor a great deal of power and control over the learner's objective function and sort of enforcing stronger fairness. And if you set it smaller, you're making the auditor weaker. So these first plots just kind of show the algorithm working, so to speak. The x-axis here is the number of rounds of this 2-player repeated game that I'm describing, and the y-axis is showing you the error of the learning algorithm's model. So I'm not explicitly representing fairness here yet. And the different curves correspond to different values of C. And so the the high-level point here is that when I let C be very large, giving the auditor quite a bit of power, the error of the learner's model decays more slowly to a worse asymptotic value, and when I make the auditor weaker, the error converges faster to a better or lower asymptotic value. These plots obscure, because of their scale, what's going on in the very earliest stages. So on the right here, I'm showing you the same figure on the left, but blown up to only show you the first few hundred iterations or so. And the important point here is that, at the 0th or first round, if you like, the learner's model is actually extremely accurate because no fairness has been enforced yet. But then as the game begins, you see there's this rapid increase in the error of the learner's model as the auditor starts to exhibit their power and constrain the learner more and more by showing more and more complex subgroups on which discrimination is being experienced, and the learner has to adapt to those subgroups. Perhaps the most important figure in the paper, though, is this one on the left, where I'm showing you for many, many different values of this parameter C, which controls the relative power of the auditor over the learning algorithm. I'm showing you what the asymptotic error was on the x-axis. This is the predictive error, and a measure that I won't go into of the extent to which there is still subgroup fairness with respect to the class G by that model. And so this, if you like, is showing you that there's an efficient frontier of models in this bi-criteria of optimization, right? So this is showing you the trade-off between the predictive accuracy or error of the learner's model and the level of fairness that's being promised to the subgroups in G. And so what you can see here is kind of what you would expect. We have a choice between making our error very small and experiencing relatively high subgroup unfairness, or making our subgroup unfairness very low and experiencing a much, much higher error. And the point of this plot is that you can see that there really are kind of palatable compromises here, right? So for instance, if I look at this area here, I'm only increasing my predictive error by something like 5% or so, and I'm cutting in half or more the subgroup unfairness achieved. So this is kind of trying to answer the question I gave before of whether this very, very strong notion of fairness can be met while still providing accurate statistical models. And at least on this data set, the answer seems to be yes. So thanks for listening. That's all I have to say. We're very sorry we couldn't be there at your workshop, but we'd be very keen to hear feedback about our paper and any discussion that ensues. And again, please feel free to reach out to us by email. Thanks very much.